So the Optimize is a new module in energyPRO. And it's free for the rest of 23 for you to test and play around with it. And it is about sizing optimization. So of course, today energyPRO optimize the operation of whatever equipment you have in your model. But now you can include that you also optimize the sizing of your equipment. And for now, it goes for energy conversion units and storages. It works with a milk calculation, and it works with a 1 year optimization period. And it works in that way that you, for each equipment, you calculate an annuity cost, which is then included in the milk calculation. And this annuity cost is calculated based on a specific investment. So that is an investment per megawatt or per megawatt hour or per cubic meter or whatever the size of your equipment is measured in, and the expected lifetime, and then an interest rate. But let me show an example I have here. It's a not that advanced example, but an example where we have a heat demand, we have a boiler, but now we would like to include a heat pump, thermal storage, and a PV plant. So then the question is, what will be the optimal capacities of these 3 new units? So for that, we go to the Optimize module, and that you find up here in the menu. Press this Optimize. Yeah, sorry, I'm in Danish right now, but I hope you'll yeah, I'll stay in Danish for now. You press this Optimize. Now, just a moment. I'll just change. I'm sorry about this. I'll just change to English. I'll do that. Just take a few seconds. I'll be back. So. Here we have it, and I'll find it again. This was this one. Yeah, sorry for this, but now we're back in English. Yeah, I press the Optimize. And then we have this window here, where you have some selections to make and some data to put in. First of all, you need to select which year are your optimization valid for, because typically if you have a design calculation, then it's only 1 year, and then that would be the year that we are calculating. But if you had like a finance calculation where you have multiple years and you have development over these years, then you can select one of these years and calculate for that specific year. Next, for the annuity, you need to include the interest rate, state that here. And then you need to select which items do you want to optimize. So we have here selected the solar PV and the heat pump and the thermal and the heat. Sorry, these two here. This is where you select the energy conversion units, and in this box you select whatever storage you might have. In this case, it will be the thermal storage. When selected those, they will appear on this list down here. So these will be filled in, what type it is, and then the name of the equipment, and finally also here the energy type. In this case, the PV can only produce electricity. The heat pump it can either you select either the heat output or electricity input, and that is, and then for the thermal heat is only heat, of course. Specify, okay, I want to optimize the size of my unit, but only up to a certain level. So here we have specified that the PV can go up to 8 megawatt, and that the heat pump, the heat output of the heat pump is up to 4 megawatt, and that our storage only up to 10,000 cubic meters. Next column, you need to specify this specific investment. So that is the investment in this case, working with euro, in euro per megawatt. For these, and for the storage, since the storage is in cubic meters, so that would be euros per cubic meter. And then you have the expected lifetime of your system. These, or in this case, we have set them all to 15 years. By these numbers here, the lifetime, specific investment, interest rate, we can calculate this annuity cost per megawatt of equipment. So, and this will then be included in the MILT calculation, and then for the MILT calculation to find the most optimal correction, you'll try to reduce the size, but still have the best result. So basically, next you press calculate optimal capacities. So it shouldn't take that long. But as you see now, it calculates for the whole year at once. It is not split into months, but the optimization period is the whole year. It's done. And now we have some numbers over here. So we found that the optimal capacity of the PV was 2.2 or 2.3 megawatt, 3 megawatt of the heat pump, and a rather small storage, actually, only 200 cubic meters. So you can now, you need to be aware of what the text says here, because when doing this calculation, we do some we take a few shortcuts. We don't consider part load power curves or minimum load power curves. So if a unit is allowed to part load and it has a minimum power curve, this minimum power curve is ignored. And if a unit is allowed not to part load, that is also ignored. So it is assumed it's allowed to part load all the way down to zero by using the efficiency at the full load power curves. Let's see how this looks. So we have a report here. I can open this, make it a little bit bigger maybe. So this optimized report, you see we have the inputs as specified. Then we have the results, the calculated capacities, and the resulting investment. And then we have the net operation income, including the annuities. So we have some revenues and we have some operation expenditures, and then we have the annuities for these 3 different units. So this was the best result that the PV could, the optimizer could calculate for these specific equipment. I could now go, it's okay there, and go to any of the other reports and see the results. So this is the result of this actually optimized calculation. So this is not the result of what you have put in your model originally, but the result of the actual optimized calculation. So then you'll be able to see, does it make sense what I see throughout the system, throughout the so like if your heat pump was you would really actually not like it to part load, then you see that, okay, we do actually have a bit of part load in some periods in this model. And likewise, you can go to the operation income, see the results, and you recognize these numbers was what was in the optimized report as well. We can go back to the optimized report, and of course now we can see how sensitive is this. So I'll just do this. I'll just open this report once again. Oh, it will need to calculate, but we'll let it do that. It'll take a few seconds. Yes, I'll just put this a bit aside, and then I'll try to say, okay, the storage, maybe we could say a somewhat higher number of years, and maybe also the PV could be 20 years instead of. So let's make a new calculation. So now you see we have a somewhat different result. Or I think I'll press this one here so we can compare the reports directly. This was with the, maybe I should zoom in a little bit. So you see now that now we have a longer expected lifetime of some of the equipment. That will of course reduce the annuity on these equipments, and therefore we will have a better result due to that. And we'll also see that actually now the PV becomes almost twice as big, or more than twice as big as it did before. And actually also that the heat pump will now be a bit bigger, and the storage will be a bit bigger as well. So we have actually more equipment now by assuming that the lifetime can be a bit longer. And you can go on and do the same stuff like with if your investment, and maybe this you have this specific investment, maybe that is not valid for the actual result here. Maybe this specific investment is valid if you have an 8 megawatt PV, and not when you have one at 4.5. So when you have one at 4.5, maybe the specific will be a little bit higher actually. Or let's just put in 7. Then you can make another calculation. So that way it's rather easy to work with, and also rather easy to see the influence of different assumptions. Of course, it is, if you have a complicated model, which in itself take a long time to calculate, you'll still need this calculation will take at least as long, or maybe even longer. So now you see with our PV has been reduced because it became a bit somewhat more expensive. So there is a bit of a, you need to do some different runs to see what's the actual optimized calculation. When done that, when you think, okay, now I have calculated the optimal capacities, then you'll need to include these values in your model, and you need to do that by hand. You need to manually say, okay, this is 3.6, or 3.4 megawatt, and you will need to put that into your PV, and likewise with the heat pump and the thermistor. That you do by hand. Yeah, I will just go back to my presentation.
Leif, sorry, there are some
This
questions
is the first
in the
version
chat.
of our optimize. We still have something we like to include in this optimize, because not all the different technologies are included yet. So this is a list of things we will include in future versions of energyPRO. The user-defined thermal storage is not included. You can only have the one where you have the cubic meters and the temperature differences. Also, hydro pumping storage has not been included. Fuel storages. And then another thing, as you noticed, you specify the upper value on the storage here, but actually that upper value is at the moment not really taken into consideration. So in a future version we will include that, so that if you have specified a lot smaller storage than I did here, and the optimal would be bigger, but then we will stop at what you have specified at the upper value. Not a small thing. We have our built-in heat pump. You can only select the electricity input and not the heat output. And then we have grid connections we like to include, and transmissions. We still have some limitation, or we do have some limitations to optimize. I already mentioned some of it. That we said that, okay, for this to work, we need to allow your equipment to part load, and we ignore any part load power curve. So it is part loading from full load down to zero. We also ignore the minimum load. And as I mentioned, this investment curve we have not included. So this is specific investment you have put in, and it's not really valid for where it actually comes out with a result. You'll need to make a new calculation where you try to put in a more precise value for that, or for that area where it has calculated. Yeah, optimization period is year, and planning period is also 1 year. Yes, I think that was actually what I had. Is there any questions or comments?
There are some questions in the group chat. Leif, can you hear me?
So I see how long the calculation time. So yeah, it is what is here is that, as I mentioned, often when you have a calculation, typically in the pro calculation, you calculate in monthly time steps, optimization period, and you could even calculate those months in parallel. Here we calculate the whole year at once, so then that itself will often take longer than splitting into single months. And if I haven't done any, I don't think we really done any thorough test of how long it takes compared with the other. But as you saw here, I don't think it takes a lot longer. But with complicated models, it will probably take somewhat longer. But if you have an optimization period of 1 year already, I think the difference will be small. Let me see. Yeah, if the result is automatically imported into the model, no, it is not. As I mentioned, you have to do that yourself. No, so another question is if the optimization module needs to have finance, and no, actually you don't. All you need, you need to operate in this. Design is actually all you need. You don't really need the finance module, but because actually there's not really any connection between what investment you can include in the finance module and the specific investment you put in here. Those two things are separated, so that's two different things. Yes. Yeah. So there's one says that he's not able to activate the optimize button. You'll need to do to optimize use the optimize module, you'll need to activate the optimize module, and that you do by activating your license. And simply you should be sufficient. Go to license and activate license, and then go through the process. And then if you have your serial number already in, it should just go ahead, and then you will have a new activation mail with a activation number to put in, and then you should be up running. Yes, another question. If it will make the interface module redundant. I'm not completely, because the optimize, as I mentioned, we have this, we do these shortcuts, full load and things like that, and only 1 year calculation. So with the interface module, you'll be able to do full calculations, like if you have a 20-year model, and then you can put in the specific capacities you will have, and then make 20 years calculations and so on. And that we cannot do with the optimize. So the thing is that you will we do have these shortcuts that we do with the optimize. The optimize is very good for getting a good idea of where to hit, in what direction, in what area is my capacities. So last question for now, I think, is if the optimization period is 1 year, is it able to optimize for interseasonal storage? So yeah, in the same way as you can do today, you can have a large scale thermal storage, and then you can use optimization period 1 year, and then you can fill the storage over the season and like the summer season, and empty it out in the winter. That will work in the same way with the optimize. Yeah, so it is only the upper level we can add, not the lower value of any conversion unit, because it's what it does. It put in this upper value, and then it part load from there down to 0, and then this upper value will try to the maximum. It will try to reduce the maximum as much as possible, but will still be able to go all the way down to 0. And next question is if what kind of information you need to put in before the optimization. You generally need to put in some values. You cannot leave like this empty. We need to have real values included with a certain size. The actual size doesn't really matter, but we need to be able to have this the power curves hour by hour, and so we need this to make a calculation. So therefore, you cannot put in an empty unit. Yes. The last question is if this is recorded, and as I said in the beginning, yes, we are recording this, and we will put it afterwards on our YouTube channel. I think I will go to the next item on my list. That will be the fuel demand. So just a moment, I will open the fuel demand model. I'll be there right away. And actually, for this one, I'll start with no, sorry. I'll start with my presentation here. Fuel demand. That's a new thing we have included in this model of energyPRO, this version of energyPRO, and that is often required when you have power to X or industrial products. We need to be able to define the fuel demand. In energyPRO, the way we have implemented it is that we technically we treat a fuel demand as an energy conversion unit. So we need, in order to find the fuel demand, when you want to insert a fuel demand, you need to look among energy conversion units. And also results will be shown as energy conversion units. And like with the optimize, it works with MILP only. So let me go to my model here. So this is one of the projects which I included with energyPRO. It's a Power to X project example where we have some renewables producing electricity. We have an electrolyzer producing hydrogen, but it also produces surplus heat. And then this surplus heat is going to heat demand. In order to make sure we cover our heat demand, we have also included a heat pump. And for the electrolyzer, we also need to put in water. From the hydrogen, that is then used in the methanization plant to make methanol. And for that, we also need CO2. And then we have a biogas production where we want to upgrade our biogas into methane to be fed into the natural gas grid. This upgrading releases CO2, and then this CO2 enters into the methanization plant. And then, of course, maybe we don't, this operates all the time, but maybe the methanization plant is not operating, therefore we need to be able to reject the CO2. But what we would like to now, I'll just make a calculation. So this is, I think it's only 1 month of calculation. And it's a bit confusing to look at maybe, but we have a lot of graphs here. We have heat electricity up here, and then we have the methanol, the CO2 consumption, and then some storages down here. Yeah, maybe I could include as well the hydrogen actually. So the hydrogen is here, where we see the electrolyzer. You also see this up here, electrolyzer produces, and then we have a hydrogen storage, and then the methanization plant takes from this hydrogen storage. But as you see here, we have some periods here where we don't actually use the methanization plant. But maybe we would like now to say that, okay, we actually have a fuel demand of this methanol, which we need to cover regardless of prices and so on. Because this one, that is an energy conversion unit consuming the fuel. But what we like to now is to have a demand, energy fuel demand. So sorry, that was not the one. This one I will add, and as I mentioned, I need to go to the energy conversion unit, and then I need to go down here. We have called fuel consumer. Then I will add that one. So it looks like this, rather basic. You select a fuel, and in this model we have quite a different number of fuels, and that will be the methanol. And I would like to have it here. You can select it in kilos, or I think I'll select in kilos per hour, and then I'll put in 100 kilos. So this is a valid. So we have a constant demand of 100 kilos. Also here, I could make formulas to simulate a varying demand of this methanol, but here we just stick with this steady demand, put it in. So you see now this is connected. I could rename it maybe to methanol demand. So what if I make a new calculation? You see now we have a different result because now we have this constant demand of methanol. So I guess you didn't notice, but before we had an income of 11.3 million or something like that, but now we have a reduced income of 9.8, and that is because this methanol demand here, we have not put in an income on that one. We could do that, and then we'll have approximately the same result as before. But since this is a demand, you don't need to put an income on it in order to have this demand to cover this demand. So that is the difference of operating as a fuel consuming conversion unit or as a fuel demand, because now this fuel demand you're forced to cover. I could, of course, make a payment, add a payment here called methanol, and then I would enter. I will go to production unit, as I mentioned, and then I'll select the methanol demand. Then I'll select the fuel consumption, and then I'll select the proper fuel, and then I could put in like 20 euros per kilo, and then we'll have the fuel demand will give an income to the model. Okay. Any questions or comments for this part? Otherwise, I will go to the next item, and that is technical in energyPRO. It's a bit related, but it's called forced operation. So this is, as I mentioned before, this fuel demand is actually an energy conversion unit which has to operate, and this is actually now included in most in all energy conversion units as well. In many cases, you have a project, a model where you want a specific unit to operate, and until now, you typically have done that by giving it some kind of artificial payment or giving it a high priority. But then that would disturb the objective calculation of the MILP. But from now on, you can define that a specific energy conversion unit is forced to operate. And this forced operation is at the minimum load of your energy conversion units. So if you have an energy conversion units which are allowed to part load and you have a minimum load included, then it will operate at that minimum load at minimum. Of course, it can also operate up to full load, but it will operate at that one at minimum throughout the period. And like with the other ones, this works only with the MILP calculation. Let me just open the proper example. Just a moment. I will find it here. Just a moment. I need to close something, and then so this model I have here is a very simple model, as you see. We have a heat demand, and we have an expensive main boiler, and then we have a cheaper boiler. And actually, this model only operates for 2 hours. So this is an operation model. So let me just see how it looks. So you see, the cheap boiler is operating, covering all the demand for these 2 hours. But actually, we want our main expensive main boiler to operate at minimum load. As you see here, we have an operational income of cost of $10. Now I go to my expensive, which, as you see, is very simple. It only produces heat, and it has 3 power curves, 10, 5, and 3 megawatt. I go to the operational, and please notice here we have a new line here, forced operation. Default, of course, is off, but then I can say it's forced, it's on. So now it's forced to operate. And as it said, it will now force to operate at minimum 3 megawatt. Let's see if I'm right. Make a calculation. Yes, so now you see we have the expensive boiler is coming in here with 3 megawatt, and then the cheaper boiler is taking the rest. You can do more. You can also select on this list down this, select a time series. Here I have only one time series in my model, but if you had more time series, they will show all here. You select one of those, and then it says, then this time series define if this unit is forced to operate or not. When it has a value of 0, it's not forced to operate. When any value above 0 means it's forced to operate. So let's have a look. So now you see, let me see, I'll just show you this time series. You see it has a value of 0 for the first hour and value of 1 for the second hour. So this means now that it is able to, it's forced to operate in the second hour. So this you can, of course, I guess you all could imagine different cases where that could be used, like if you have an boiler which can only operate, which is forced to operate during the day but not during the night, or vice versa, or something like that. You can implement this functionality, and this does not affect the. It's not a part of the. Of course, you should see we have a worse result than we had before when it was a cheap boiler who did all the production. But since we are forced to operate this unit, we will have a slightly worse result. Yes. Just a moment now. I will like to go to the next example. I just need to look it up. Yeah, so any comments or questions for this? Okay. My next item is these new time series function that we have included. We've had this TS mean for many years, which finds the mean, the average value of a time series for a given period. Now we have included new functions, TS max. Will find the max value, of course, for the same period you give of the time series, and the mean, and then the sum from the time series. Beside that, I would also like to show you that we actually have some date and time functions in energyPRO, in the time series functions, which can be very usable. They are not very well documented for now, but I think we'll improve that in the future. But I would like to present them anyway. So I'm just making ready. I have here another energyPRO model. As you see, it doesn't contain a lot. It only contains a number of time series. So we have a time series. In this case, it's spot prices for 22. And then we'd like to treat these time series. We like to find some minimum, the mean, max, and summation, and so on. To illustrate these, I will use this time series overview. So here you have an overview of your time series and your time series functions. I will just make sure that make them a little bit nicer to look at. So I think we are here. So we have the time series. So we can already here see in this time series what is the minimum value, what is the max, and what is the mean. Next, we have these functions here, as I mentioned, the mean, the mean, and the max, and the sum. These three parameters. It needs the name of the time series, and be aware here, typically it is a symbol that you would need. But in this case, with these functions, it is the name of the time series. So it is not DK1 spot 22, but it's DK spot prices 2022, as it says here, you put in. And then the interesting part is the start and the end of this period you want to find in this case, the mean for. And that can be defined in a number of different ways. As you see here, you can either put in this date number. Every date has this 5-digit number. So this number here is the 1st of January 2022, and this one is the 1st of January 2023. So then that will find the mean of this period, and as you see here, this is 1629 equal to this value here. Another way to specify this date is to use a functionality called calc start, calculation start. So that takes the start of your calculation, and then here I added 365 number of days in the year, and then I have the same period as up here. So I put in date calc start, that gives 1st of January 22. Date calc start plus 365 gives the 1st of January 23. And as you see, this is the mean. So therefore we have the same number here as we have in the original time series. Another way to illustrate, to put in dates, is you can put in in more like this. So here you put in the apostrophes, what do you call it, and then you say 1st of January 22, and you need to put it in the format of your system, of your computer. So this is how my computer reads dates. Maybe you use months first, and then date, and then year, or year, months, date. Then you'll need to put that in that order, in that way. But basically, this one is I guess mainly the most readable. And this one was the max value. And you see this max value corresponds with the max value of the time series. And finally, the summation here. that it takes simply sums up the values throughout this period. So basically, it is this value here multiplied with the number of hours in the year. But this was now we have specified a fixed period, but you could also have like a more a rolling mean or max and sum and so on. And same way you use the name of the time series, and then you specify this underscore, and then it says -1. So that is if we say the time is now 1 o'clock, then it's 1 o'clock yesterday it starts, and then +1 it will be until 1 o'clock tomorrow. So it will take an average of these 2 days. We can have a look to see how it looks if we just take these two and show them together in a graph. You see here that the hourly fluctuation, and then we have this smoothing out because we have the average for 2 days. So that will go like this throughout the year. And of course, likewise with if we take a look at the minimum, it looks a little bit different, because now it will find whatever minimum there is in this two days of period. So that we have more straight lines typically. And likewise, we could select them. We can do it like this, and then we can see all of them. So you see this, the maximum and the minimum. So this was for kind of rolling. But another interesting thing I have included here ways to calculate a monthly mean and a daily mean and a weekly mean. The monthly mean, I use this formula, and it looks a little bit complicated, and I guess maybe also it is. But here I use another functionality in energyPRO, or date, this encode date. The parameters for that is you have 3 parameters: specify year, specify month, and specify day in month. So what we want is we want to start at the beginning of the month and end at the end of the month, of course. So we say, okay, once this underscore that represent where we are, and then the year is all year is 22. Then the month will be, if the month is January, then that will turn 1, and then we say the 1st of January 22. And then we need to find the end, or the 1st of February. So we say, so here it becomes a little bit complicated, because here we need to take into account that we have, when we shift from one year to another. So if the month is 12, we will need to add 1 to the number of years, so then we will be 23. And then next, if month is 12, then the month part will be 1. And then we end up with the 1st of January 23. If month is not 12, it will be the same year, and the months will be +1. So let's see if this works. You see, we have the same value here. I'll try to make a little longer. So you see here, we shift 1st of March, we have another value. And I could try to select the whole year. It's not that easy to see maybe, but we do have up and down, but monthly values. So that is a neat way to find a monthly mean or monthly max or whatever of these functions you would like to use. So I have made a daily mean here and another new functions which are not very well documented, but we will document it eventually. This is this floor functionality. And the floor is because this underscore will be this, like this date, then dot some decimals. Well, decimals illustrates the hour of the day where you are. So, but then the floor, it goes down to 0, down to the full number. I guess you could also have write an integer, then you will have the same result. So this is down to midnight, and then +1 midnight next day. So you see here we have different values for each month, each date. Yeah, and I will move forward. We have also the last day of weeks. You can include that, and then you'll be able to calculate the weekly mean. So we see here we have a shift here at the Monday, a shift at the next Monday, and shift at this Monday. So I guess this day of weeks, I think depends on your computer settings. I'm pretty sure. So if you shift on Sunday, then it will recognize that. Yeah, I think that was what I was supposed to tell on. I would like to tell on these time series functions and these possibilities for using these dates functions or parameters. If you're interested, I could forward this example to you, but please just let me know. The last item of today, I just need to see what happened here, like this. It is private wire functions. And just a moment. I will. I'll make it ready. So the private wire functions have been available in the function in the economy, but you'll need to have enabled the German CSP law. But now we have made them more general available, and they now are included in the MILP calculation, so that depending on what values you put in and how you specify it, it will affect the MILP calculation. I will just show you. Let's see if I make it here. No, just a moment. I'll need to open the model. Here we are. So this is a rather simple model as well. And it's mainly for showing how the income is changing. I don't think in this model we actually do a lot of changes in the calculation itself, because we have these renewables, and then we have an electricity demand, and then we have had some payments, some revenues up here. If we start with the operation expenditures, we have an income, an expenditures on the import electricity, and we have some operation and maintenance. But then we have these payments here, and this is this private wire EP exported. That is, you can find them when you make a user-defined payment. They are on the list down here on production unit level. You see them here. We have these two. We can either have an income of covering own demand or having an income of exporting. So this case, and then you specify as a parameter the energy conversion units. So in this case, we have an income for the PV to export of 10 euros per megawatt, not much. And for the covering own demand, we only get 3. We go to the wind. It only gets 5 for exporting, where the PV got 10. And the wind actually get more for covering own demand. So if we make a calculation, now it goes through the months. Okay, so what we see here is also a new, well, it's not new, but in the last version of energyPRO, the 4.9 we released summer, we had the option of including the payments in the production graphic, so you can see how much did this payment actually give me an income or expenditures. So here we have put in the revenues of these 4 payments which are presented. So you see them each here. So let's just select a period here. You see the red one is for the PV exported. So you see, even though that the PV is actually well below the demand, all the PV is used for the export because that was the most beneficial. We got 10 euros for exporting the PV production, and you see we get 0 for covering own demand, and that is because we are exporting the whole PV production. But then we have the wind turbine. It covers the demand, and then the remaining production of the wind turbine is then used for the is then exported, and you get an income from that. So that is very simple what you can do with these payments, and you can use it for controlling which units are allowed to cover internal consumption and which are not. Like in many contexts, you say that renewables are only allowed to cover the electricity consumption of heat pumps or electric boilers. The thermal CHP units are not allowed to cover this demand directly, but is only allowed to export. Otherwise, you will need to pay some extra taxes. All that you can control with these private wire payments. That was very brief, but I think we are running close. So I think that was what I had. Any final questions or comments or anything I missed? So if no further comments, I think we will. I would say thank you for all for joining in. And as I said in the beginning, this presentation will be available on our YouTube channel in EMD YouTube, and then you can see it through there as well. Okay, thank you very much.